Okay, let's try to derive, at least I'll sketch a derivation of why the Poisson probabilities actually look as they look. That's something we may just take as a matter of fact, but let's try to touch on why that actually comes out like that. So let's have a look at, assume that we have a time interval going from 0 up to capital T. And what we're interested in is the random variable, which is number of events in the interval 0 to t. This is the one that we would usually, at least under some assumptions, say this would be a Poisson distribution when we count the number of events in a period of time. Now, a way to sort of prove this, at least to some extent, is the following. We would like to find the probability of, the probability distribution of this one. What is the chance that we get exactly x? And we want to show that this is the Poisson. The way we do it is to divide the time interval into a lot of small intervals. One of these intervals we would call delta t, and which means then the number of intervals will then be capital T divided by delta t. So we divide it into n intervals. The same to say that capital T is then n times delta t. And we assume that this random variable, the number of events, comes with some intensity. I call it lambda like in the Poisson, but for now it's not necessarily Poisson. We're just going to prove that we end up there, but still we're just saying that there is some average sort of number of events during this time period from 0 to t. Then there are actually some assumptions that should be okay. So the real situation where we would apply the Poisson distribution would assume this to be true in those situations. Let me point those assumptions out. We have assumption 1, that we could say that things are constant. The intensity, the chance of seeing events are constant over time. So we get the constant probability of, you could say, success in those small intervals. So you could say the probability of success in a small interval, probability of success. Events, sometimes we use the word successes, that's the same as events for me now. The probability of success in such a small interval is constant. And what would that constant then be by sort of common sense? This constant would be the average number of events over the full time interval divided by the number of, so we split it into those small intervals. There are n of those. So on average there would be like this in each individual time interval. So that's the constant assumption of homogeneity, you could say, that it's not like we have one intensity in one end and another intensity in the other end. It's the same intensity across the whole thing. That's the first assumption. Second assumption, we could say, I'll just write independence. Independence, it means that events does not influence other events. That's the short of that. And the final assumption is that basically only, you could say roughly, only one success at a time assumption. So basically it's the assumption saying that there cannot be really multiple events at exactly the same time. They can be very close, but they cannot be exactly on the same time. Another way of stating that event is that the probability of success in a single of those small time intervals is, I should say the probability of having more than one success, because in a Poisson, of course, you could have more than one in small intervals, but when you make the intervals very small, you assume that basically this probability will become negligible, so almost zero. So that's the assumption of not sort of multiple events at exactly the same time. Given those assumptions, we can prove that this probability becomes the Poisson. And here it comes. A bit of technicality to make it happen, but nevertheless. This, you could say that this probability, actually, I should say these assumptions here, sorry for jumping, these assumptions would imply that the binomial distribution can be used. We have the same p throughout, and all the time we throw a coin to see whether we have an event or not, and there could be only one. It's the same probability. So that's the assumptions of the binomial. So we state that the relevant probability is given by the binomial using the underlying p of success in a single experiment, which would be lambda over n to the power x, 1 minus lambda over n to the power n minus x. Maybe we should say this is not exactly equal because due to, the fact that there could be more than one success in a small interval, actually, you could say there would be some rest here. But this rest, let me just right away sort of ignore it, because this rest will tend to 0 when we let n tend to infinity. Letting n tending to infinity, like having more and more small intervals, is like making the intervals smaller and smaller. And due to assumption 3, this rest will disappear. So the whole exercise now is, since the rest disappears, this probability will be the right probability, but we'll have to realize to look at this part and see what happens when n is tending to infinity. That is kind of a mathematical analysis challenge here. What actually happens here? We need to rewrite it just a little bit to realize that. Here we go. We say that the probability is, we rewrite the binomial coefficients as follows: n minus 1 down to n minus x plus 1. Since we have cancelled out part of we still have the x faculty, but I have cancelled out the n minus x faculty. I've removed, you could say, sort of the remaining terms here from the binomial coefficient. I then also take, if we look at this term up here, I remove the n to the power of x. I put that here, n to the power of x. Then I'm left with lambda to the power of x, and I just sort of repeat. Let me, for this part, just repeat the final term here. And since this here tends to 0, I will now ignore this. We'll need to do one more step before we can identify what actually is happening when n is tending to infinity. I will take each of those xn's. I actually use those for each individual term up here. I have 1, 2, I actually have x terms up here. So I will take each individual of these xn's, and I will say the first one becomes a 1, dividing by n. The second one becomes 1 minus 1 over n. Look at this term. I divide n by n, and I divide 1 by n. And I obtain this term here. And I do that for all the terms, 1 over 2 over n, down to 1 minus x minus 1 over n. So this is the binomial coefficient, actually, I have here. Then I collect these two terms and say lambda to the power of x over n to the power of x. No, I have done a mistake here. Actually, it's this term I'm lacking. It's the x faculty term, because I already used the n to the power x term. So we put the x faculty term here. And then I'll split the last term, and that's the final thing. I put it in two parts, lambda to the power of over n, to n, and then 1 minus lambda over n to minus x, like this. Now we can see what is going on when n is tending to infinity, right? This one, of course, is 1. What happens here when n tends to infinity? Well, this term will tend to 0, so this will go to 1. Again, this term is going to 0. So the entire term will go to 1, so on and so forth. All of them goes to 1. This one, I mean, is not having an n, so we just repeat what is there. This term, look at n. This one again tends to 0 when n goes to infinity, so that's an easy part. 1 minus 0 is 1. 1 to the power of anything is 1, so this goes to 1. And finally, the last part here, this one, we would recognize something from mathematical analysis, namely one of the representations of the exponential formula, which is saying that e to x can be expressed as the limit of n going to infinity of 1 plus x over n to the power of n. And if I use this classical representation of the exponential function, I see that this term tends to e to minus lambda, and you will recognize that all that I'm left with here are now exactly the Poisson formula. So this is the proof of why the Poisson probabilities appear like this.